In the manual, we have looked at what happens when our transmission line is either left unterminated, so open-circuited, or when there is a short circuit at the end of the line. We've looked at what happens when we send a pulse down a short-circuited or open-circuited line, and also we've looked at what happens when we use a step voltage at the input of such lines. In this tutorial, we will be looking at this in a bit more detail with the simulator. We won't be looking at the detailed setup of the circuit schematic to achieve this with the simulator. However, this simulation file will be available to you. But we will be looking at how, by changing the pulse width and the length of the line, we observe differences in the reflected and incident pulses. So we start with the case of an open-circuited line. We send a pulse down the line at time equals 0.5 nanoseconds. So at 0.5 nanoseconds, our generator starts producing the pulse. And then the pulse travels all the way down the end of the line. And of course, because in this case we have an open circuit, the voltage pulse gets reflected in its entirety and comes back to the generator. So in this case, because of the length of the line, by the time the pulse has reached the end of the line and come back, the generator is no longer producing the pulse. So our pulse width here is 0.2 nanoseconds, is sent down the line, but then it takes it a longer time to come back, which is about 0.5 nanoseconds, and hence by the time it comes back, the original pulse that was being produced is no longer there. However, if the line had been shorter, or if the pulse width had been wider, we would have seen something different. We would have seen an overlap of incident and reflected voltages, as we'll see shortly. So we can clearly see from this graph that the pulse gets produced at this instant in time, 0.5 nanoseconds, and comes back at about 1 nanosecond. Now we can insert markers to see this difference a bit more accurately. We can press Ctrl M and put one marker right there, and then we can press Ctrl M again and put another marker right there. Now, to see the difference between these two markers, we just have to change one of them as being the reference. And this is easily done in Microwave Office. We just right-click on the marker readout and select Reference Marker. And now you can see that the delta between this point and that point is about 0.5 nanoseconds. So for the pulse to travel to the open-circuited end of the line and back, it takes 0.5 nanoseconds. This is the round-trip time, so to get the time that it takes to travel to the end of the line alone, we have to divide this by 2. So if we divide 0.5 nanoseconds by 2, we get 0.25 nanoseconds, and if we assume that we are traveling at the speed of light, then the length of the line will be 0.25 nanoseconds times the speed of light, and this turns out to be 75 millimeters, which is exactly what the length of a line is. Now let's get rid of these markers, and we will tune the width of the pulse and the length of the line to see how this affects the reflected and incident voltages. And first of all, let's start changing the length of the line. As you can see at the moment, it is 75 millimeters, which is exactly what we calculated. Now, if I decrease the length of the line, you'd assume that the incident and reflected pulses would get closer together, because it would take lesser time for the reflected pulse to come back. And if I increase the length of the line, the opposite would happen. It would take longer for the pulse to come back. Now, if I increase the width of the pulse, what is going to happen is that by the time the reflected pulse comes back, the incident pulse may still be produced by the generator. So if I increase the width to a certain point, you can see that we get to a stage where by the time the reflected pulse comes back, the incident pulse is still there. And so what you see at the observation point is a superposition of incident and reflected voltages. Because they have the same polarity, this translates into a doubling in the voltage amplitude. And this is what we've seen also in the case of a step voltage. If you have a pulse width that is really, really long, in effect you're getting yourself into a very similar situation to that of a step voltage being produced by your generator. This is the typical way that a time domain reflectometer works. You actually send a step voltage and then you wait until the step voltage is added to the reflected voltage. In this case, because we have a doubling in voltage, we know that there is an open circuit at the end of the line, because we know that when there is an open circuit at the end of the line, the voltage gets reflected in its entirety and with the same polarity. Yet again, we can work out the length of the line just by looking at the difference in time between this point here and that point there, which is exactly the same as what we did earlier, which will give us the round trip down the line and back. Now let's move on to the case of a short circuit. In this case we have exactly the same setup as before, but the only difference is that our line is terminated with a short circuit rather than an open circuit. Again, you can see that we have an incident voltage pulse here, and then we get a reflected pulse right here, which has traveled all the way to the end of the line, had its polarity reversed, and then has come back to the observation point. Now remember that when you have a short circuit, as we have seen in the manual, the polarity of the voltage is inverted. However, the amplitude is the same, because the voltage gets reflected in its entirety in terms of amplitude, just as it did in the case of an open circuit. Yet again, we could work out the length of the line by using the markers as we did before. For example, we could press Ctrl M and put a marker right there, and then Ctrl M again and put another marker right here, and then we can just make this marker the reference marker, and we can see we get a delta of 0.5 nanoseconds, divide that by 2, and you end up with a line of 75 millimeters as we did before. Let's get rid of the markers. Again, because the pulse is only 0.2 nanoseconds wide, and it takes 0.5 nanoseconds for the pulse to reach the end of the line and come back, by the time the reflected pulse comes back, the incident pulse is no longer there. However, if the line was shorter or if the pulse width was longer, then we would see an overlap of incident and reflected voltages. Now we can open the tuner and tune the width of the pulse and also the length of the line. You can see that the length of the line at the moment is 75 millimeters as we've calculated, and now if I decrease the length of the line, the two pulses get closer to one another, and if I increase this, then the incident and reflected pulses move further apart. If I increase the pulse width, I'll get to a point where the incident and reflected pulses add together, but in this case, instead of getting a doubling in voltage, you're getting the voltage coming down to zero, because the incident and reflected pulses have got same amplitude but different polarity. So you can see yet again the way that a TDR system works. If it finds a short circuit at the end of the line, after the round trip that it takes to get to the end of the line and back, the voltage will then drop to zero, because the incident and reflected voltages will add together and they are of opposite polarity. In the case of the open circuit instead, we saw a doubling in voltage. In this case, we see the voltage going down to zero. Yet again, you can look at the difference between the 2 points and get the round trip time, which then allows you to work out how far along the line you find a short circuit. The other interesting case to look at is when we terminate our line, whose characteristic impedance is 50 ohm, with a 50 ohm termination. In this case, as you can see, there is absolutely no reflection down the line. We are using exactly the same length of line, and as you may recall, at the 1 nanosecond timestamp, we used to get a reflected pulse. In this case, we get absolutely no reflection whatsoever, because all the power is transmitted to the 50 ohm load, which is at the end of the line. Now, if I open the tuner, and if I tune the length of the line, you can see that there is absolutely no difference in what happens here, and also if I tune the pulse width, yet again you see that there is absolutely no difference in what goes on, because there is no reflected voltage at all.